All right, we ready? Today we're going to start talking about a type of force system that is called a non-concurrent force system. So these are different than the ones that we've covered up till now, and here is how they are different. Okay? All the problems that we've covered up till now have been of a particular variety, whether or not we have realized it. They have all been of a variety where, if you look at all the different forces applied to particular objects, like the case maybe of a weight hanging from ropes, okay? One of the things that you could say about this particular type of a system is that if you look at the line of action of all of the different forces that act on this body, what can you say about all of those lines? They all intersect at a common point. Okay, there's one point where they are all intersecting. What about the case of like a drum? This was another category of problem that we've looked at, right? We've got a drum maybe sitting in some kind of a V-shaped cradle, something like this. Okay, if you look at that drum, where are the forces acting on it? Well, you'd have weight happening here. You might have a contact force happening here and another one happening here. Okay, what can you say about all those lines of action? Okay, all these lines of action will intersect at a common point. All right, so all of the things that we've looked at up till now, these have been the category of problems that we have been dealing with. So today we're changing that. Okay, we're going to do a completely different idea of how these problems work. What if you have a body, and these bodies can be, kind of shaped however you want them to, so I'll just show a more complicated shape here. And let's say that you have a body like this that has a pin that holds it down. What does that pin do as far as the reactions at that point? It restricts it to do what? Okay, it can only rotate. It is not allowed to move left and right. It is not allowed to move up and down at that point. Okay, so let's say you have that. Let's say that you also put on like a roller up here. And let's say that we put on a couple of forces as well. Let's say that I put a force here. And I put a force here. Okay. What would my free body diagram look like? I'm just doing this kind of in a conceptual way for right now. Okay, the free body diagram might look something like this, where we have what reactions at the pin. Okay, rotational is the one reaction we probably don't have, right? We have reactions happening vertically and horizontally because these basically represent forces that we know must exist there if it is not going to be allowed to move in those directions, right? There have to be forces there that will be whatever value they need to be in order to prevent movement at those locations. Okay, that's what we mean by reactions. Okay, and then we'll also have a force up here. What does that roller do? How does a roller behave? Okay, parallel to the surface as it rolls against, right? Well, that's where the action happens. Actually, the force, though, happens perpendicular to the surface that it rolls against. Okay, so there would be a force there, and then, of course, this force that I identified down here, it kind of goes down like this. Let's look at all these lines of action. There's a line of action of this component of force. Goes that way. There's a line of action of this component of force that may coincide with that one, right? And then we have this other line of action of this force that goes up like this. Do they all intersect at the same point? And I think the answer, is fairly obvious. No, they don't. Here's the other one that I'll deal with right here. So we have several intersections, right? We have an intersection right here. There's one point where they intersect. There's another point. Okay, there's another point right here, and another point right here. So one quick comment before we move on here. If you have all of these forces acting on here, what is possible for this body to do that wasn't possible for the other bodies, or wasn't really something we had to worry about for the other bodies, might be another way to say it. With these kinds of problems, the one where you had just a weight hanging or a drum in a trough, there were no influences that would make it want to rotate, right? All of these forces all interact at a common point, or all the lines of action all intersect at a common point. It means there's nothing that's really there that would cause this body to want to rotate, right? Or this body to want to rotate. What about this body? Okay, with this body, it's got a much bigger probability that it might want to rotate, right? And that's what happens whenever you have lines of action that intersect at not all a common point. So up here, these were concurrent force systems, and this is a non-concurrent force system. And you know, sometimes this is, you know, you might see it as being more that you've got to deal with. The other way of looking at it is another tool in your toolkit to be able to solve things. But what we can say about these is that if we sum up all of the moments acting on a non-concurrent force system, there is actually a version of Newton's law that is used for rotation. It basically says the sum of all moments has to be equal to the polar moment of inertia, and a letter that's used for that a lot of times is J, multiplied by, what do you think alpha might be? What was Newton's second law when we were dealing with translational movement? Yeah, F equals ma. Well, it turns out that Newton's second law has a rotational equivalent, and it's if you sum up all of the moments acting on a body, then that is going to be equal to the polar moment of inertia times, what do you think alpha might be? How about angular acceleration, right? How fast it picks up speed. One example you could think of for angular acceleration is that when you take off from a stop at a stoplight, your tires of your car start out not rotating, right? And then you need to start moving, and the speed of your tires gets faster and faster and faster, right? So that's angular acceleration for that to happen. If we have a body where we know that there is no angular acceleration, which that would be a statics problem, right? So we say for statics, we say that there is no angular acceleration. And what does that allow us to do? Yeah, the sum of moments has to sum to 0. Okay, and I'll tell you this as well. We are going to restrict all of our problems in this class to being two-dimensional problems. So since we're on two-dimensional problems, the only kind of rotation I could be talking about is about what axis, around what axis. Okay, the z, if you're actually, you know, if you think of this being in the x and the y direction, if this body was going to rotate, it would have to rotate around an axis that would stick out of the board, right? That's the axis that it would actually rotate around. And so whenever we think about these moments, they are actually moments about a z-axis, one that is going out of the board. And that's what we actually saw when we dealt with the cross product last time. We saw that there was, you know, when you summed up all of your moments, it created a moment around a z-axis. Okay? So that's what we're dealing with these non-concurrent force systems. And what it means is that now, instead of just having the sum of forces in the x direction having to be equal to 0, and the sum of forces in the y direction having to be equal to 0, we actually add another constraint that we can use for non-concurrent force systems, and it's that the sum of moments around the z-axis has to be equal to 0. And for two-dimensional problems, this is our set of constraints that we can use for that, and this allows us to basically come up with 3 equations if we want to completely specify that a body is in equilibrium both translationally as well as rotationally. Okay? Shall we do a quick example problem? Let's do it. Okay. So I'll do a relatively classic type of example problem. Let's say that we have a body that is just sort of an L-shaped body, something like this. Let's say that over here, this body is constrained from translation, both left and right and up and down. Okay, and let's say that over here we have a roller, kind of like the one that I drew on the last picture. And now let's say that I've got a force that is pulling on this body. Maybe it's pulling right here. And let's say that it is pulling so that it, I don't know, let's make it go this way. Okay, so it's pulling at an angle here. What do you want that angle to be? 20 degrees. Okay, sounds good. And what do you want the force to be? 120 pounds. Works for me. All right, and so we need another couple of things as well. How far is it from the pin to where these two forces happen over here? How far is that? Okay, 3.5 inches. Okay. The other thing I'd like to do is how far is it from the pin up to the roller? 2 inches. No, that seems too much. How about 1.5? Now, there's a little bit of a level of precision that we kind of have to figure out the level of precision we're at. Does it matter that it looks like I attached this force right on this corner, and how that basically relates to this pin over here? Okay, so in one sense, I have given you the distance from the pin to this surface, so that direction's okay. What about vertically? Does it matter that there's a little tiny bit of gap right here? And let me say this. The practical answer in terms of doing engineering problems, whether that be on your homework or whether that be for fundamentals of engineering exam, or whether that be, whatever kind of engineering problem you end up doing that is sort of a school-based problem, it's not necessarily a real-world-based problem. If you're doing that kind of a problem, what you can essentially go off of is, was I given enough information to be able to handle that, right? If it doesn't give you that information, what do you think your best shot is? Say it doesn't matter. Say they probably didn't mean for there to actually be a gap in that direction, right? But if it does give you information about how high that is right there, what do you think that means? You probably should use it, right? These are the kind of the tips and tricks that matter for school that may not matter for real life. In real life, it probably wouldn't make much difference whether or not you handled that little bit. But if you want to try to get it to a high level of precision for a academic kind of a problem, that's kind of how you can deal with that. So do you want to count it or not? No. You want me to not count that? Let's not count it. Okay? But I think it was still worthwhile mentioning that that's how you can kind of process these mentally, and whether or not you need to account for something as far as your academic problems. In the real world, let me just say this, that's going to be part of your job if you go and practice engineering somewhere. You're going to be the one who decides whether or not those kinds of things are important, right? And how do you decide that? Trial and error. Kind of trial and error. I would say it based on your experience, right? After a while, you get a feel for certain things, and you decide this thing matters and that one doesn't, right? And you start doing some of that stuff by feel, right? And that's not a very satisfying answer probably right now for anyone, but that's kind of the truth though, so I figure I'll go ahead and say that. All right, let me also do this. Let me put some letters on here. Let's say this is point A, let me call this point B, and let me say this is point C. Okay? Now, I want to figure out how much force does the roller apply to this little bracket, this little L-shaped piece, and how much force is applied at the pin, at A. Okay? So that's what I'm supposed to find. And one way I can shorthand that, I can call these external reactions. Okay? Why do you think these are external reactions? Okay, these are basically forces that are applied to member ACB, right? They're forces that are applied to that coming from the outside. And they're reactions because right now we know how it's being constrained, we just don't know what the force values are that it takes to make sure it's constrained. Okay, so that's what we want to solve for these external reactions. What do you think we should make as our first step? Yeah, that's a good idea. Let's do a free body diagram. Doing a free body diagram for these problems is not any different in terms of the steps as it was for our previous free body diagrams. So what do you want to start with? You isolate what? Like you decide what body you want to put on here. You isolate it. You draw it separate from everything else. Okay, that's step one. So now what we've done is mentally, we have converted our original problem into one where this little dogleg shaped piece is now floating in space, right? No forces are acting on this body at this point. Now what do? Okay, we go back in and we replace the forces that it would have had on it, but we put them on with force vectors rather than just understood from what the attachments look like. So what we're going to do at the pin, because it is not allowed to move left or right, I put on a reaction here that I'll call RAX, and a reaction here that I will call RAY. Okay, I've kind of implied in those names is the idea that I'm going to be using an X and Y system like this. So I'll go ahead and take the opportunity now to put those on here. Now what? Okay, so point B, is that what you said? What happens at point B? The force should point what direction at B? All right, like this, right? Because there's a contact force between that little roller and that surface. I'm going to call that just R sub B. Why am I not putting a vertical arrow as well at that point? Yeah, a roller only reacts normal to the surface that it rolls against. Okay, now what? Okay, yeah, I can copy that 120-pound force down here as well. And I'll go ahead and say that it's, again, at that 20-degree angle. Okay, what else do you think it would be good to copy over? Distances, okay. So we can copy over the 3.5-inch distance that it is from here to here. And we can copy the 1.5-inch distance from here to here. Okay? All right, so we have three things we don't know. Is that correct? We don't know RB, we don't know RAX, and we don't know RAY. Okay? Since there are three things we don't know, it can be helpful for us in order to solve this and not always end up with a system of equations we have to solve. It can be helpful to think a little bit critically right now at this point and ask ourselves a question. If we get a chance to use these three relationships, right? We know that the summation of forces in the x is 0, summation of forces in the y is 0, and the summation of moments around the z is 0. These are the three we get to use. Which of them might be the most efficient to apply first? Okay, someone says y. Okay, and why do you say that? Okay, and I actually really like that reasoning. What she says is that there are only two forces that have y components, and of those two, only one of them is unknown, right? So we could very quickly write an equation for the y direction. In which case we would have RAY pointing up, and then what as far as the 120-pound force? Is it the entire thing? Okay, yeah, it's going to be pointing down, so it will be negative. 120-pound. Okay, and we want the cosine is the suggestion. Why do we want the cosine? Okay, yeah, what we want is the component of that force that's adjacent to where the angle's measured. Okay, so I'll put cosine of 20 degrees. And these are the only two force components in the y direction. So I can set that equal to 0. That means that RAY is equal to 120 pounds times the cosine of 20 degrees. And I'll go ahead and put that in here. Okay, that's 112.76 pounds. All right, it did come out positive. What does that mean? Okay, that means the direction we assumed it was by drawing it vertically upward on the figure. That means that was correct. Okay, what's next? Do you want to sum forces in the x next or not? Okay, someone says no. Why would we maybe want to avoid summing in x right now? Yeah, we still have two unknowns that act in the x direction. We don't know RAX and we don't know RB. Okay, so since we don't know either of those yet, if we do a summation of forces in the x, we won't be able to solve it because it's got to have two unknowns in it. So it might be good for us to do another equation first, if we can, where we only have one thing that we don't know. Okay? And so if you look at the only other one we have to choose instead of fx is summing moments. Okay, can that help us? So the question we got to ask ourselves is there a place on this diagram where the lines of action of two of my unknown forces, two or more, right, intersect at a common point, right? If I've got two or more lines of action of unknown forces intersecting at a common point, it is likely that that's going to be a really good point to sum moments around. Why is that? Okay, so on this one, I don't know, well, I actually do know RAY now, but, you know, let's actually say that I picked this point right here. Even if I hadn't already done the original equation, picking this point and summing moments about it neither RAX nor RAY will produce tendencies to rotate about this point. Do you agree with that? Okay, because their lines of action actually pass through that point. Okay, so that's a really good place to sum moments around. So let's do that. And this is how we usually denote that when we're getting ready to write it. We usually go ahead and say we're summing moments, and we put down here a point that we're summing moments around. And I always like to do this too and make it explicit what direction I am taking to be positive, kind of like I do for my translational versions of the same thing. So what all creates moments around A? What are all my forces that create moments around A? Okay, RAY, RAX do not create moments around A because they have lines of actions that pass through them, but RB, okay, would have a tendency to create a moment around point A. What direction? Clockwise or counterclockwise? Counterclockwise, so I can probably leave it positive and multiply by what length? Okay, 1.5 inches. Why that? That's the perpendicular length from the line of action of RB to point A. Okay, you can kind of see that if I was to draw that line of action like this. It's 1.5 inches from that line of action to point A. Okay, what else do we have that would create a tendency to rotate around point A? Okay, my 120-pound force does, but do both X and Y components of the 120-pound force do that? Okay, that actually depends on how we answered that first question that I asked you up there, right? If we had to consider that little drop that happened right there, then yes, both X and Y would create tendencies to rotate. But if we're saying we can ignore that little discrepancy right there, then only which component would create a moment around that point? Just the Y component, okay? And so what we can do, we've already figured out what that Y component was. It was this 120-pound cosine of 20 degrees. What direction, by the way, does that tend to try to rotate it? Clockwise, so I do minus 120 pounds times the cosine of 20 degrees. And what else should I multiply by? Okay, someone suggests 3.5 inches. Okay, and what is that? Okay, what we did there is we found this vertical component, right? The line of action of that vertical component is 3.5 inches from point A. So we use 3.5 inches there. Do we have anything else that tends to create a rotational effect around A? Okay, I'd say that, you know, given the fact that we're ditching the effect of the horizontal component as far as its rotational effect, we can just set this equal to 0. And that allows us to solve directly for R sub B. That's just going to be 120 pounds times the cosine of 20 degrees times 3.5 inches all over 1.5 inches. Okay, so 120 times the cosine of 20, times 3.5. Okay, all this divided by 1.5. And that gives me 263.1 and that's going to be what units? Pounds.
So how do you figure out which like forces to use, like RB
Okay, I have to pick off any force component that would tend to create a rotational effect around A. Okay, so if let's look at an example of like a fence post, okay? And I get a chance to either push with 200 pounds on the top of a fence post sideways, or I weigh about 200 pounds, I stand on top of the fence post. Which of those two actions that I do on the fence post would create a tendency to try to rotate the fence post? Okay, here's the fence post. Okay, is it going to try to make the fence post topple over if I just stand on top of it? Okay, and I weigh about 200 pounds, I push on it like that, it doesn't tend to create a rotational effect. Okay, the other possibility is I could push on it sideways with the same amount of force. Is that going to have a tendency to try to make the fence post topple over? Yeah, so that creates this rotational effect where the first one where I was pushing straight down on it, it didn't. Okay, the difference between the two is that the line of action of the first one passes through the point where the rotation would occur around, right? Whereas the line of action of this other one has a space, like there's a length, there's a non-zero length in between that line of action and that point. And so what we're doing in the case of this bracket here, we are trying to figure out which of the force components have non-zero lengths between their lines of action and the point around which we are evaluating the moments. Yeah, if there's a length in between the line of action. So let me do this. I'll show you the other component that's acting here. Right? Those are the two components of the 120-pound force. Well, we said at the very beginning that its line of action was close enough to passing through point A that we were going to ignore that effect. Okay? So that's how we knew that. All right, we have one last piece to do, right? We've come up with two of our three external reactions. What is our last piece? Okay, we're going to sum forces in the x direction. I'll take rightward to be positive. I have RAX, correct? And what else? Okay, I have RB. Should it be positive or negative? Negative. Is that it? Okay. I'm taking rightward to be positive. RAX, based on how I've shown that arrow, it points to the right, so that one's positive. RB points to the left, so that one's negative. Okay. What else do I have? I do need the x component of the 120-pound force, right? So I need to put that on there as well. Should it be positive or negative? Negative 120 pounds times what? The sine of 20 degrees. Okay? And I think that takes care of all of my force components in the horizontal direction that would, or all my force components in the horizontal direction. So what do I do? Okay. I take my value that I got for RB and I plug it in, and then I solve for RAX. Okay, so what that would give me here would be 263.11, right, plus 120 times the sine of 20. And that would give me 304.16. Pounds. All right. Questions? Yes, ma'am.
So for the moment, you made counterclockwise positive, and then for everything it should be right.
Correct. That's absolutely cool, okay? So one is a moment, the other one is a force, right? So, and it's important to keep those separate, right? The idea on the moments here is not that any particular force is one direction or another. It's that the effect of the force with the length, does it make it go clockwise or counterclockwise, right? That's what you're evaluating in this case. In this case, it's a pure translational effect. So you do just look at if it's pointing right or if it's pointing left. Good question. Okay, anything else? So this is a nice warm-up. You ready for actually working hard now? Yes? Yeah, look at how excited you guys are. You're like, you want to do another problem, an intense problem.